we have anticipating problems and managing short-term safety issues. So that's the goal, turning this data into information, and dam surveillance overall is going to help us. Now in this first today's session, we're going to focus on this part, dam monitoring, so gathering data, just so that you can put it in perspective. So very quickly, we can gather data and collect data manually and in an automated way. The good old direct manual readings is the ones where we go to the sensor. We can access physically the sensor and collect a manual reading. For instance, this is a pendulum. You can see it's an inverted pendulum. Here we have the tank and the cable going into the foundation, and this is a direct pendulum next to it. We have the reading plates. We can go there and gather the data directly. So it's a direct manual reading. Maybe we have a seepage gauge, a weir. We can go there and make a measurement of the water height over the weir. So that's direct. In this case, it's going to be very important to make sure that we have proper conditions, because dirt, lightning, having proper lightning and moisture, all of these are going to affect the quality of our readings and the quality of our data. And then we're going to have temperatures. We're going to have piezometers in the foundation. We're going to have inclinometers. With an inclinometer, well, it's somewhere in between. We're going to have a probe. We're going to put it into the inclinometer casing. But if we're talking about a piezometer, a temperature sensor, it's going to be an indirect manual reading. So we're going to approach an enclosure, the casing, these closets we have, even in the gallery or outdoors, and we're going to go with a measuring device with a readout unit. We're going to plug in some cables and make a indirect manual reading. So just keep this in mind, because these are different ways of gathering data. And then we're going to have the automated readings. So we're going to have automated sensors, let's say a piezometer. Then we're going to have the indoor and the outdoor enclosures. In this case would be an indoor in a gallery. We're going to have this casing, this little closet, an enclosure, but we can have them outdoors as well. The signal is going to go from the sensors by means of cables to these enclosures. And then we use fiber optics to go from the enclosures to a CPU, a central processing unit, which is it's a computer. It's a personal computer that is just devoted to gathering this data. It can have software tools, and then from there, we usually have communication devices so that we can send that information to central offices, mobile phones, in essence, access the data real time. So this is what is making up an automated reading. Okay, monitoring campaigns. So now we've put in perspective the dam monitoring. We've talked about direct, indirect manual readings and automated systems. Let's go now for monitoring campaigns. And I'm going to go right for the issues. So we don't have much time, so I'm not going to go into checklists and all let's say, the paperwork that we can have to carry out the manual readings. I'm just going to go for the issues. We're going to have direct readings, such as this one, where oftentimes we're going to be needing proper lights, proper lighting. The place has to be properly lit. This is very important. We're going to have readings where there's going to be a lot of moisture, water coming down and pouring down into, in this case, a pendulum or maybe joint meters. So all this moisture is going to impact the quality of our data. Another type of manual readings is the indirect, where we go to an enclosure and we connect in a readout unit and we take the measurements and we write them down. So this is a manual, indirect manual reading. Also, having a proper place, a chamber, somewhere where the operator can go and carry out its duty properly. We're going to have topographical campaigns where oftentimes we're going to have to, right there you can see there's somebody with a total station up there. You can see it's like a kind of a berm in really a slope. So dangerous place, difficult access to go there to have and carry out a topographical campaigns. These are real issues we face on a daily basis. And then we're going to have the automated readings. So again, this is an enclosure that we would have indoors in a dam gallery. And you can see that we're going to have a PLC, which is probably too much. In this case, this is a Siemens PLC. Usually we're going to find data loggers. So data logger is going to allow us to gather the data in these enclosures. And also we're going to be able to program some routines like, okay, gather all the piezometers 8 o'clock first thing in the morning, and then 16 hours in the afternoon, and send them to the CPU and the central the offices. We're going to have vibrating wire interfaces. So this device right here is a device that it's going to gather vibrating wire. It's going to carry out the Fourier transform, and it's going to create a digital signal from the analog signal coming from the piezometer, from the total cells, any vibrating wire device. We're going to have multiplexers. This is like a traffic light that is going to tell the system. It's like a traffic manager. So which signals are reading? We are reading at a certain moment. So this set of piezometers, this set of thermistors, this set of load cells, whatever. This is like a traffic light for the automated system. We're going to have sensor inputs. So we're going to be able to come here with a readout unit and take out manual readings right here for the calibration of the automated system, something which is essential. So calibrating the automated system. We're going to have electrical surge protections, power supply, and then the communication systems. In this case, is fiber optics, and a document folder where we're going to put here the report, the drawings, where all of this is laid out. Now, we also can find automated systems with an outdoor enclosure. So this is the downstream slope of an embankment dam. This is an enclosure. It's a closet, outdoors closet with the protections. We're going to have all these things we talked about. So the PLC, we're going to have the fiber optics, the power supply. This is the electrical surge, multiplexers, everything. But on top of that, we also have this, which is a little, enclosure within the automated closet enclosure, we're going to be able to plug in our readout unit, select piezometers, load cells, and carry out manual readings. Of course, these are indirect manual readings. Remember, we're not accessing the sensor directly, but these are going to be manual readings for calibration purposes. So this is my favorite and to me the perfect automated enclosure. We have the automated system, but we facilitate and we make things easy for the operators just to take manual readings. So in essence, remember, if we have automated readings, it's very important to calibrate that on a regular basis, at least once a year. You need to go there and calibrate that with a computer and see exactly the signal we're getting, compare that with the manual readings. And even so, I'm talking about calibration here. I'm not talking about manual campaigns. So even if we have an automated system that we calibrate every year at least, we need to carry out manual readings. For instance, if we have an automated pendulum, at least every fortnight, every 15 days, we want to go there physically and take a manual reading. Apart from this calibration, so and oftentimes we go there and we take manual readings and then we compare. Seepage gauges, every week at least you want to go there and carry out a manual reading, a manual measurement, even if you have the system automated. So you're gathering real-time data every moment. You can go with your mobile phone and click on the button, and it's going to send a signal, and it's going to send you the seepage reading at that moment. And even if you record the data every other 15 minutes, but once a week you want to go down the gallery and take a manual measurement. So this is key. Even if the system is automated, we can never replace manual readings and calibration. And of course, the readout units. We can have like this wonderful Camel vibrating wire analyzer that even gives us PDF reports. But this is a manual readout unit. We go there, we can read thermistors, we can read and vibrating wire and resistors. So we can read anything with this, and we can stabilize the signal. If we have noise, if we have an old piezometer, it's going to be able to gather the data. This is a manual readout unit, excellent one. It's like the remote of the TV, so very small, portable, incredibly efficient. But many dam owners are using nowadays tablets and mobile phones. So you go on site and you carry out the campaign, you write it down, but you do that on a tablet or on the mobile phone. And if you have communication and a wiring system inside your gallery, it's going to be recording the data real time. So in Spain, Iberdrola and Enel have the systems, and so it's a manual system, but it's making the task really easy for the operator. And we can have telemetry. So a system where we have piezometers or this is a standpipe piezometer. This is going to be sending real-time signals, but even so, from time to time, we go there and we gather manual readings. Okay, so once we've got the framework, we've talked about direct, indirect manual readings, monitoring campaigns. Now we go for the nitty-gritty. And I'm going to now go really fast, just to give you some comments on sensors, and then we'll devote the last 3 minutes to new technologies. So in general, this is not a totally, I'm not including here all the sensors and all the controls we can have in a dam, but it's just a starting point. We're going to have sensors to control and gather data on external variables. So reservoir levels, ambient temperature, rainfall, humidity, evaporation, just let's say external to the dam body. We're going to have hydraulic controls, uplift, pressures, piezometric levels, pore pressures in embankment dams and foundations. We're going to do that with many different types of sensors. So Casa Grande piezometers, open standpipe, vibrating wire, Carlson, different sensors and transducers. And we're going to have seepage. We're going to have thermal controls. We want to control concrete and seepage temperature. We're going to have deformation displacement controls with horizontal variables with pendulums. There can be many different ways. So optical ones, and of course the good old traditional ones. We can use also control these horizontal displacements with topography. And topography now is enhanced with 3D scans in SAR from satellites. But we can really control with many devices. Oh, well, liquid settlement systems, this is for vertical, sorry. This should go here, so we'll change this. This is for vertical, leveling liquid settlement systems. Of course, in the foundation, we'll have rod extensometers, tilting, joint and crack meters. We're going to have geological and straight up layers, and we're going to be willing to control that. Unit strains with embedded extensometers, load cells, soil extensometers in embankments and embankment dams. Then volume control for concrete with strain gauges. And of course, dynamic seismic controls with accelerometers and a seismograph. So all of these, out of these different types of controls and sensors, I'm going to try and give you some quick tips and comments. Reservoir levels. This is a key parameter because we need to compare and relate any control variable to the reservoir level. Anything. Concrete dam, masonry dam, embankment dam, whatever type of dam, we always need to compare and relate our measurements to the reservoir levels. So we need redundancy. And measuring the reservoir levels is not simple. We need to have a reference point. So the topographical elevation needs to be very clear. And this is not clear in many instances. So we need to know exactly the topographical levels because that can change from time to time. And we can have inconsistencies in reservoir levels because the reference or the crest level is different depending on the sources. And this is real issues that we face on a daily basis. We can have the best system, which is this hydraulic system where we have a direct connection between the reservoir level, this pressure, and a transducer we have in a gallery that it's getting directly this water in this tank, and then we are transforming the pressure from the water column into the reservoir level. This is the best system. But sometimes you cannot have direct access to the reservoir level. Maybe it's an old dam. If it's an old dam, this is not that simple, drilling this, and you go for the good old pneumatic system where you have a compressor and you have a pipe, and this bubble has to counter the water column, so that way you turn that into the pool level. We can have radar systems where we go to the crest of the dam and we have this probe, this pole, and with the radar we measure how far is the water from this point at this elevation. We come here with topography, we know this elevation with accuracy, and we can assess reservoir level in a certain range. And we have the transducer pressure system sensors. So we put this transducer, this is just a weight, a dead weight on the cable, and we drop this to the bottom of the reservoir, and this way we measure water levels. And of course, the good old analog system where we have a scale and we have a look with binoculars. Watch out if this scale is in the spillway. So this is the wall of a side wall of a spillway. So when the water is flowing here, we're going to have the surface, first surface of the reservoir dropping. And so this is going to impact our readings. Beware of reservoir levels that we take because of pressure connected to the outlet works. So you can see many different ways of measuring reservoir levels, but it's such an important parameter that we need a lot of redundancy. Weather stations. So we're going to find this as well in our dams. It's very typical to have next to the offices a weather station so that we know ambient temperature and evaporation, wind. So just good old meteorological parameters. And now we go into the dam. So we're going to have seepage weirs and gauges. They can have different shapes. If it's a very small seepage rates, it's going to be a triangle. If it's more bigger flows, it's going to be rectangular. They can be manual, so we have this scale that is not touching the water. So we drop it, then we measure the water height over this this weir, or we can have this. This is like a ultrasound system that is going to measure that in an automated way. And here you can see both the ultrasound system and the manual scale. And important things. Well, we need to make sure, number one thing, that it's clean. So this canal that approaches the weir has to be cleaned on a regular basis and maintained. So this is important. If we have an ultrasound system for an automated system combined with a manual reading scale, we need to make sure that the water is still. So if we have any kind of distortion in the water surface, this is going to have an impact on the quality of the automated data. We need to make sure that this is leveled. So you can see this line, this red line is a laser. So with a laser, we can exactly relate this height of the weir here to the scale so that we have an accurate measurement. If we have some kind of outlet within the weir, we need to clean it up and make sure that it has no seepage itself, so that we're not losing water underneath. Also, if we have scales for manual readings, we want to have them with a device that allows us to turn it and tilt it so that it's not touching the water when we're not taking measurements. Like in this previous example here, just look at the scale. The scale is on a regular basis, it's not touching the water. So we release this and we put it in the water only when we're going to make the measurement. And we avoid this. eventually it gets dirty. Okay, piezometers. We're going to spend a couple of 3 minutes, 3 to 5 minutes here with piezometers. So piezometers are used to measure the pressure. So piezometers don't give us water levels. Water levels is a different thing, is an observation well. So it's a borehole, and that's going to be an observation well, and we're going to measure water levels, so phreatic levels. If we want to measure pore pressures, we need a piezometer. Now, so the piezometer is really can be two things. So the piezometer can be like the transducer, that's the sensor, the transducer that is gathering a physical variable. So the vibrating wire piezometer, that's the sensor with a transducer that it's going to gather a physical action, in this case, the water pressure, and it's going to turn it into an electrical signal. So that's the transducer. But when we talk about a piezometer, we also think of a system. It's just a whole system. And we're going to have different types of measuring devices, electrical ones, vibrating wire, fiber optics, hydraulic, pneumatic ones. We're going to have cables, we're going to have casings, pipes. All of that is going to be the system. So we need to be able to tell them apart. And we're going to see that also with vibrating wire piezometers, we're going to have the traditional good old installation and the fully grouted method. Okay, so just like I was mentioning, the piezometer is a system. We're going to have the measuring device, so the sensor, the instrument, but then we're going to have other things. So we can have pipes, we can have the cables. So that's why when we say piezometer, we need to just tell apart when we're talking about the instrument and the system. So here's a system where we have a vertical pipe to access the pressure in the foundation. We're going to have this manometer, which is a Bourdon gauge. It's a measuring device, so a transducer. And then we're going to have also a vibrating wire connected to the pipe. So we have two types of transducers of measuring the pressure. And all of this together, the borehole into the foundation, the short borehole, the pipe, this vibrating wire, this Bourdon manometer, all of this is going to be the piezometer, which is a system. Okay, we're going to use them for many different purposes, to control pore pressures, heave. So I'm not going to go into details. And then we're going to have different types of piezometers. So just some quick ideas for you. The Casa Grande piezometers. The Casa Grande piezometers are standpipe. So we're going to have a porous plastic or ceramic element that's going to allow the entrance of water, of pore pressures here, and several pipes. And these pipes are going to be connected to the atmosphere. So it's going to be... yeah, it's going to be...
request to the participant, kindly mute your microphone, please.
Yes, thank you. And so in the Casa Grande piezometer, this element, this porous element, is going to be surrounded by sand, and we're going to have a bentonite seal, and then we're going to access the top from here. And they give us the pore pressures in these layer, in the foundation. Of course, we cannot measure negative pressures. But then we're going to have other types. So we're going to have the good old vibrating wire piezometer with a cable. We're going to have the pneumatic and hydraulic piezometers. These are old systems, but we're going to find these in many dams, so we need to be aware of them because of that. we're going to have fiber optic piezometers. So this is a fiber optic sensor. And when I say fiber optic here, is not just the cable, but the sensor. The sensor itself is different from the vibrating wire or from the pneumatic or hydraulic diaphragm. In this case, it's going to be fiber optics, the transducer, the sensor itself. And of course, a vibrating wire. So this is the one from Encardio, the Indian manufacturer. When we go to closed piezometers and especially the vibrating wire piezometers, it's going to be in a closed enclosure, in a casing. We're going to have the cable, we're going to have these connections. So these piezometers are the most robust and efficient. We're going to have a very quick response time. So they're going to be perfect for clays and silt materials. We have to watch out for lightning when we have lightning and a thunderstorm, because that can damage our piezometers. We're going to have to watch out for the cables, these connections and the quality and the features of the cables, and also for being overranged. And we're going to have factors and issues with vibrating wire piezometers, so drift in the signal. We talk about this in a session afterwards. Now, for the closed piezometers in our dams, the good old type with a manometer, it's a short borehole that goes only 1.5 meters into the foundation, or a couple of meters. So this is an open a pipe that's connected to the foundation, and it's going to transfer this pressure to the transducer here, which is a manometer. We're going to be able also to open this taps and even measure seepage. But if we close it, we're going to measure the pore pressures here in the dam body foundation contact. We need to be careful to know this elevation here and the elevation of this contact or dam body foundation. Because if this gallery is 15 meters above this contact, when we are measuring the pressure here, that is the pressure up here in the gallery. So 15 meters above the contact. That is not the pressure we have at this point. So we're going to have to account for that in our calculations. So watch out for this. Then with vibrating wire piezometers, which are the most typical ones, some things to remember, very important ones. Cables. We need to specify the features of these cables. I cannot go into details, but this is key. Many problems with piezometers, with vibrating wire piezometers, are caused by cables. Zero readings. So this is the zero reading when we're about to install this piezometer. This is very important because all the readings in the future are going to be determined by this zero reading. Connection in cables. So the piezometer is here. It has a short thread of cable here that needs to be linked to the cable that is going to go to the enclosure, to the closet. This connection here is also critical. It needs to be done properly with resins, so watch out for this. Filters. Our piezometers can have high and low air entry filters. We need to choose and pick out the right one. Do not use high air entry filters in fully grouted piezometers. And also account for the pressure range and the specifications. This is very important. The pressure range is the maximum pressure that the piezometer is designed for, including the installation, because many piezometers are damaged during the installation because we go over the range. Watch out for this. Always go for the minimum range of the sensor and have some safety factors, but don't. We need to pick out the range, the reading range of our piezometer. The resolution, which is the smallest increment that we can read. So this is determined by the readout unit and is described as a percentage of the full scale. The accuracy, so it's the degree of closeness of our measurements to the true value that the transducer is getting from the physical signal, the pressure in this case. Also, watch out for the long non-linear effects, because if we're reading in a range, in an area where our piezometer is very non-linear, we can have errors and discrepancies. Of course, the calibration range in temperature and the operation range. Watch out for this. Okay, quick comment on the fully grounded method, which is perfect. Go for this if you can. But just be careful if you have different strata, different layers with very different hydraulic conductivities and permeabilities, because then the fully grounded method can give you problems. But if you have a continuous, homogeneous layer, go for this. This is more efficient. It works perfectly. And this is proved. So it's scientifically proved. There are no issues. But of course, it has to be properly installed. And you have to carefully choose the features and the installation procedure and everything. But this is completely feasible, and it's been proven. So there's been a lot of controversy for years, but this is no longer an issue. This is very clear. Unless you have different strata with very different conductivities, the fully grounded method is there's no problem, and we can have multi-point piezometers in the same borehole. Okay, so we leave piezometers and we go now to another type of sensor or parameter control, drainage. Don't forget maintenance. Drainage systems, either the dam body drainage like this one, which is coming from the top of the gallery and connecting galleries, or the drainage in the foundation like this one, and this is in the foundation. We need to maintain it. We can clean it with a pressure device like this one, and from time to time, every 5 years, if it's a limestone with a lot of clogging, or every 10 to 15 years, we need to re-drill the drainage, either the dam body or the foundation. When I say dam body, of course, it's a concrete dam. We don't drain the embankment, but I'm thinking about concrete dams. And watch out for sedimentary rock foundations, because we can have issues like this. The drainage system is given us is eroding the foundation, even if it's a concrete dam, but sedimentary rocks can be tricky. So watch out for these issues. And remember, we need to carry out maintenance. Yes, Kalpana, were you saying something? Okay, well, I'll just go on. So temperature monitoring, we go to another device. We can have, again, different devices. We can put together different sensors. We usually use thermistors, which are very accurate nowadays. We can even go to 0.1 Celsius degrees. And this is where we use them for. We can have thermocouples, are the ones we use during construction in RCC and concrete dams, and RTDs. RTDs is really any device. So thermistors put together in a thread, a cable, are really RTDs. But these, we can go for different types. So we can measure that with our resistors, or in this case with platinum sensors, transducer that give us the highest accuracy. But we're usually going to use thermistors. Pendulums used for horizontal movements in our dams. We can have inverted ones where the tank is up here, the cable goes into the foundation, and direct pendulums with the anchor next to the crest and is going down. Issues, moisture, corrosion, not having proper lights and lighting to make the readings, the oil that's in the tanks that is lost and is no longer there, water impacting. So all of this is going to impact the quality and the robustness of our readings. I'm running out of time, but Louis has to excuse me because I'm going to go beyond 5 minutes of the time I had. Okay, topographical and geodetic campaigns. Go for proper pillars with isolated. So where we put our total station is isolated with an outer concrete isolating device. Then this leveling device that it's going to get rid of a lot of errors. Also for calibration and leveling, we're going to have these elements on top of the dam. Make sure that your pillars are on ground, sound ground, so that we have no issues. But these are important things. Rod extensometers, very difficult to have proper and robust readings with rod extensometers. They give us deformation in the foundation, so it's epsilon. So it's an incremental displacement divided by a length in the foundation. So if the unit is no unit, it's really incremental length divided by a length. So it's epsilon as strain in the foundation. We're going to have lots of issues. Water and humidity coming from the foundation. If we have transducers, either if this transducer is a capacitor, is a resistor, is an LVDT, watch out for humidity conditions in the foundation. Maybe we want to have like a drain so that water that's coming from the foundation is not to impact our transducer. Watch out for the device we use for manual readings that needs to be calibrated every campaign, and how we make measurements also the on-site. Allow, even if the system is automated, allow for manual readings always. Soil extensometers that we can have in our embankments and a chain of these devices. Joint and crack meters, watch out for humidity and moisture impacting. Maybe you want to have like a roof to prevent your automated system from being impacted. We're going to have also this nuts in, and this is a joint in a concrete dam. So the measuring device, this is for a free 3D joint meter. Make sure that this is properly connected to the dam. Strain gauges in concrete dams. Also, we can have different types. Also, the dummy you want to have in this case for volume analysis in concrete dams and arch dams, you need to have the dummy strain gauge as well. Hydraulic, vibrating wire, and magnetic settlement sensors that we can have in embankment dams. So lots of issues during the installation. We need to be careful for many things, also for the magnetic rings, the hydraulic settlement sensors that from really, this is a transducer, we install it, we put it in a concrete device in the middle of the dam body. Then we need to cover these and watch out for the clay core. Then we're going to have a chamber. So many issues until we get a proper reading. Inclinometers, remember, and in place inclinometers, the casing, the types, go for ABS, plastics, and the probes. Also, lots of issues that we can have with inclinometers. We could spend just one long session just on inclinometers, and then seismic response that needs to be connected with a GPS, a real time. All these sensors need to be connected. We can have in the foundation, in the galleries, on at the dam crest. We need to account for also lots of details when we go for the seismic response. So just know that this needs care, design, and analysis before we make the installation. And finally, a very couple of minutes just for the new technologies. So along with the good old traditional sensors, the new technologies, they're not that new anymore. So we've had this for many years. So fiber optics for seepage controls in embankment dams. We're going to have the fiber optics. We're going to have a distributed control of seepage. Drones, that we're using drones for taking pictures, thermal analysis, scan, and have a 3D scan of our dams and visual inspections for in a very remote areas where it's difficult to go physically. So drones are helping us. So all of these are dams and dam owners using drones. Fiber optics, again, in this case for control of temperature in concrete dams during the construction, but then during operation, it's a distributed. It's not just one point, but a whole line of to know the thermal gradients. GPS combined with pendulums. You can see the signal from the GPS, differential GPS and pendulums, very useful in this case for an arch gravity dam. Radar, interferometry, INSAR, it's been readily used in many dams for displacements, and we can have campaigns every week. So as opposed to topography. So this is a very powerful tool, and the accuracy is getting much better. 3D laser scanner, we have now an accuracy of 1 millimeter. So for large dams, this is also an interesting option. Ambient vibration-based dynamic monitoring. These pictures are from Louis. So this is another so-called new technology, very useful. Of course, INSAR, not just for the dam, but also for slides in the reservoir rim. And then finally, new technologies that allow us to stabilize vibrating wire and thermistor signals that with old devices cannot be measured. Data loggers that are incredibly powerful, Ethernet, internet connection, communication devices, multi-point. In this case, our thermistors. So this is an RTD for temperature measurements, but we can have also multiple piezometers. So this is something that was not possible 10, 15 years ago, 10 years ago. This was not possible, though. This is new. And of course, telemetry. So these are all good new technologies that we have at hand. And I'm sorry because I've used a bit more time that I had. So sorry, Louis, for this. But yeah, there was a lot to be covered in this first test session. But I hope that we've gone through very quickly. We could have spent just these 2 days on these topics. So, okay, over to you, Louis. And sorry for we'll just take a little bit from the breaks.
No problem, Manuel. As you said, we could spend basically 2 days or 3 days on this, which is very important.
Yes.
But thanks
Absolutely.
a lot for I think a really good presentation.
Yeah. So
okay,
over to you.
Yeah. Good morning, everybody. So And actually, before I start my presentation, I was listening to Manuel's presentation, and I thought maybe there's one important aspect that I don't think we covered in our program, which I just wanted to touch on, and it's a whole thing about Manuel, you were talking about range, but also the whole aspect of you need to know what is the range that you're going to actually get on site with your dam. And I get it especially a lot with concrete dams, that people use technology, for instance, to measure displacement, and the accuracy of the type of technology or the instrument is actually larger than the actual displacement that you want to measure, if I can put it that way. So
Yes,
I get
very
it a lot
typical.
here in Africa and South Africa, that people, for instance, use surveying methods. They claim they have a millimeter accuracy, but they use normal surveying techniques. Then if you go, for instance, if I normally say, well, if you go and monitor the movement of the foundation of a dam, I want 0.1 or 0.2 millimeter accuracy. So even if I had a millimeter accuracy from the technology, I'm not going to actually see what I want to see. But these guys claim a millimeter accuracy. I think they're closer to 10 millimeters accuracy, to be honest. So for years, they spend effort and money to do these campaigns, and they do this monitoring, but the accuracy is actually not, and then they will come back and say, I don't see anything, because your accuracy is actually more than what you expect to see from the behavior of the dam. So that's really a problem that I see in my world.
Yeah.
A lot of designers, especially on the design side, install instruments and use instruments, and it's not appropriate for the actual the parameter that we measuring, and what the sort of the range in the parameter that we actually expect from the dam, and that's really something to focus on. So yeah, and I don't think we cover that really in any of our subjects that we've set to talk about. So sorry that I just sort of throw that in there as well.
Yes.
But
Well,
yeah,
at least in the for the piezometers, it was at least thrown there. But
no, but why when you were actually showing for instance, the crack meters? So I know there's a lot of people that use like a very coarse method to monitor the displacement in a joint or a crack. And if you look at the concrete gravity structure or even an arch, okay, you need to be able to measure 0.1 of a millimeter accuracy. If you go to a millimeter accuracy or 2 millimeters, you will not see anything. Because
absolutely.
your displacement that you actually, if you understand concrete and you understand it's a very stiff material, your range of displacements are maximum a millimeter, in most cases, if I can put it that way. So
and tilt sensors
and
as
the
well.
tilt and the same. So that's why you need to understand what's the accuracy and what your structure is really going to show you. My case histories that I talk about later on concrete, unfortunately, I didn't include one of those to actually show it, but never mind. Okay, let me go on with my presentation, and I actually called it data acquisition and management. All right. It's talking about all the things that Manuel, that is in our program, but I was just trying to summarize it. So I'm coming back to what I showed you guys yesterday. And the whole concept is we want to build knowledge when we do surveillance. All right, but there's something also very important. And when I was doing these presentations, that I see at a lot of dams is this concept of a data file. All right, but Manuel, I think, was talking about it yesterday as well. and I talked about it as well, it's so important to actually have all the information pertaining to the dam and all the documentation from planning, investigations, design, construction, operation, maintenance, surveillance, all the measurements. You need to actually look after this information. Okay, it is extremely important for you, and that's the knowledge part that I've been talking about. So it's really important, and in my world where I work, dam owners normally don't give this enough attention. Okay, so either they have this information somewhere in a store, a document store, and you go in there and you can see nobody's in there since the dam has been built, and nobody knows where what is, and it's not well referenced, and it's difficult to actually find information. So in most cases, it's really a good idea to digitize, to start digitization so that you can access it. But there's also issues if you actually digitize it. Please make sure that, for instance, if you digitize drawings, I mean, this is an example here in South Africa where a dam owner paid a third party to come and do the digitization. And as you can see, they didn't do a good job. And unfortunately, they actually destroyed their hard copies. You cannot believe it. So now we sit with information that we can't really read and see what's actually happening there. I know it sounds like a sort of a simple thing, but really then the other thing is backups. So, and also, if you've done the digitization, if you can, please don't destroy the hard copy, the paper copies. All right, just keep it if you can, keep it. All right. Then the next thing, and we also talk in our, if you go and look at our bulletins, we talk about a briefcase, and we also call it a data book. So that's like really a summary of pertinent information. And why we want this is if you have an emergency and you need to get an expert or a specialist in that doesn't know the dam, that person must be able to actually access all the pertinent information to make a decision what needs to be done if it's like that. And I've been to 2 years ago, I've been to a very big dam here in Africa, Arch Dam, 180 meters high. And as part of a panel of experts, we got there. Their information was based in the head office, and we were only at the dam. So they had issues with their network, and basically for a few days we were sitting there and we could not actually access the information. So I was just thinking, if this was an emergency, it would have been an absolute crisis. We would not have been able to actually access the information and make decisions on what to do in case of an emergency. So really also important for every single dam to have a data book with all the pertinent information so that you can, when there's an emergency, that you can have a look at it. Okay. So if one actually looks at some general monitoring requirements, and Manuel has spoken about it, but I'll just sort of touch on it. So one of the most important thing is to make sure that you do, if you do manual or whatever type of observations you do, that you actually stick to the recommended sort of frequency of these observations. Okay. It's very important, and I'll talk a bit more about to do error checking, to do proper record keeping, essential to do interpretation. But I think coming from our examples that we will show later on, I'm going to show you some really importance of proper interpretation. So let's just quickly looking at, so I normally do, if I go and it's a big dam with lots of sort of different types of instruments, I normally go and see sort of the frequency. Many people do that, but you don't really get a feel for if the people doing it are doing it at the right frequency. So I normally actually look also, and I determine the frequency and days for this particular dam. These are pendulum readings. The operating staff is supposed to taking it weekly, okay? And you guys can see now in the last 10 years, the frequency is really actually started to go down. It's a very important dam and it's got issues. So one can actually, it's a good way to look at it. This is the same drainage, and you guys can see in this for like, even especially those 3 years, they didn't do drainage monitoring at all, which is shocking. To be sorry that I'm calling it shocking, but it's so important for this that proper drainage monitoring is done. So I'm showing you guys also maybe just ways how you can that you can include in your sort of evaluation system if you're using a sort of a third-party system or your own system, build something in there that you can actually see the frequency of your campaigns. So the other thing that for me is normally important is some terminology that we use. And the most important one here is the term metrology. Okay. And if you go and actually look what's the definition of it, it's normally defined as the art of taking measurements. So if you take manual measurements, but to a certain degree, yeah, but especially with manual measurements, the different types of manual measurements, it's really an art to take these measurements. One of the issues that I see a lot of times is people, an operator is new at the dam, he gets handed over a readout unit, whether it's something manual or a semi-manual one. He just gets given it and he gets told, go and take a measurement. He's got no idea how to do a proper measurement. He goes and does it the way he or she thinks they should do it, and you actually don't get a good quality measurement. All right, so it's really an art. So it's really very important to spend the resources and the effort to actually train the people well that's supposed to actually be taking the readings. Okay, so how do you do proper measurements? Okay, Manuel has talked about it. So the first thing is to do calibration. Most of these real manual readout units, I mean, you showed the rod extensometer ones. It is essential to have an installation or a method every single time that you do a reading, that you do a calibration before you start your campaign and after you start your campaign. I mean, you can knock your readout unit or you can just drop it and it won't work anymore. I've seen it so many times. People, not just months, years, they will actually use a faulty readout unit for years and nobody actually discover that there's something wrong with the readout unit. So you've wasted all the effort and you actually don't know what's going on in your dam. Okay. The other important thing is you have to have a uniform procedure. Okay. So you're supposed to actually describe that. I normally recommend and help dam owners that they compile a standard operating procedure when they take manual readings or they take readings at the dam. And you train the operators that does that they actually perform these uniform procedures. It's extremely important. So even the time of the day when you take the readings, okay, and how you do it, it's very, very important. It has an influence on the quality of the readings that you actually get. Then the other thing is you have to, if you, and I'm sorry, I'm talking now a lot about manual readings, if I can put it that way. But validation of the measurements, I see it so many times. People go out, take a reading, one reading. They don't even take multiple ones to make sure that they actually have a stable reading. They have one reading, write it on a piece of paper or in a book, and that they never actually validate it. They wait for the expert to get in 5 or 10 years' time to have a look and see if things, and then like every 6 months or once a year, they type that all into their database or their spreadsheet. That is remember, we actually, the purpose also of this monitoring is to make decisions if there's a problem. Remember, I showed you guys the failures that one has. You want to immediately use the results of your surveillance, your inspections, your monitoring. You need to act immediately. If there's something that shows that there's a problem, you can't wait 6 months or a year or 5 years, because you most probably will have a failure. Okay. Then the other thing, and I was just talking about it, when you do readings, I normally ask the people if I do training for people, this subject that I'm talking now about, I normally have a practical session with actual instruments that we do readings and things like that. And it's amazing, as I said, the bad habits that a lot of people have, they just take one reading. And in many of these sensors that Manel was talking as well, especially the older ones, vibrating wire, the first reading you take might not be the right reading, if I can put it that way. It might take 1 or 2 or 3 readings to actually get to a stable reading, if I can put it that way. So you need to take multiple readings. I normally say at least 3, and those 3 need to be the same value. If you don't get, you carry on taking readings at that instrument until you get a stable reading. Doesn't matter what it is. And if you can't have it, okay, then it's an issue. It's not to say that your instrument there's a problem. Well, if we say instrument, it could be your whole setup that has a problem. Okay, but very, very important. Then the other thing that is very important is when you do monitoring, doesn't matter what type of manual monitoring you do, it's very important to actually record who's responsible for the observation, what's the info on the readout unit. Extremely important. I've had so much experience in this that I get on site and then I see a jump on readings. Okay. And then you ask the person and they said, oh yeah, no, we had a new readout unit there, but it's nowhere is it recorded. So if that person that's still there, that has that knowledge, if that person is no longer there and you have to go and look at the information, you would actually think suddenly there's a jump in the readings and there's something wrong. Okay. Then again, calibration reading, you have to record that. Okay. And also have a comments section. Doesn't matter what system you have, whether you have a hard copy system, whether you have a cell phone system, where you have a whatever system, it's absolutely essential to make sure that your system that you actually use, where you record your measurements, really includes this. Okay. So if one actually looks at your data management, this is a typical sort of flow that one would get in your data management. So you will have raw data, whether it's a manual reading and whether it's even an automatic reading. It starts off with raw data. And for instance, in a vibrating wire instrument, okay, it might most probably a frequency that you actually get. So, but you still need to verify whether that is in the right range that you expect. Then you would go and actually do, normally this verification, you actually do it on site. The best is to have a reference to the previous reading as well, what was taken, if you do a manual reading, for instance, so that you compare it. So say in your vibrating wire, if you had the frequency of 3000 previously and now suddenly you read 5000, you know there's something, either that you have a real problem or there's something wrong with the reading. So you should do it already on site. Then you normally would do conversions if you need it. I mean, Manuel was talking about, for instance, a pendulum is already a displacement that we get, but a lot of the instruments, other instruments that we use, like piezometers and things like that, we need to convert it. There's a conversion that needs to happen so that you actually convert it into engineering results, into pressures or displacements or whatever. Okay. So, and that database is very important. Normally, actually, the front part is also done in this database. All right. I want to just mention it already here. I've seen some suppliers have systems and they will chuck away the raw data. They only store the engineering results. And that is an absolute no-no. So if you deal with a supplier, and please interrogate the system if you want to use their systems, you need to store the raw data. Absolutely essential. And I'll get to it now. Don't delete or change anything in the raw data ever. That is, yeah, just keep it like is. All right. So just the other thing, if you have a database, have multiple backups. Okay, really have multiple backups. You cannot allow the information to get lost by a computer crash or anything. Okay, please make sure that you have multiple backups. All right. I've mentioned it. Please never edit the raw data. All right. You can do editing afterwards. You can edit your results. You can decide not to use certain values and so on. Never edit the raw data. All right. And I'll show you some case history why I say that. So then on the data verification side, okay. And that's also a sort of an art more than a science, if I can put it that way. So most people that has done that. So please do it with caution. I've seen it, and I'll show you an example now of what people did. They did verification. They made an assumption during the verification, and then they said, well, this information doesn't make sense, and they wanted to throw it away, or they didn't give it any attention. Okay, so you must really take care. And my good colleague that Chris Oosthuizen, that he was and mentor that I grew up, he used the words like massage, manipulate, and tweak, if I can put it that way, in the data verification. So sorry that I might use this. It's non-engineering, but it's something that every single time you need to apply your mind and be clear why you do it, and also record these decisions if you want to actually make changes during this verification, not to your raw data, but to a data set that you want to work with. All right, so be very careful with that. So let's just quickly look. This is a 75-meter high arch dam here in South Africa, and it was completed in 2000. All right, it's got some vibrating wire piezometers that measures the pressure in the foundation, because we want to know whether the grout curtain is still and the drainage system is still working. Not a very good installation, okay? Unfortunately, it's got issues with corrosion. I mean, Manuel was talking about it. I started being involved in this in 2015. So this dam has been in operation for 15 years. And when I started, the only thing they had was a spreadsheet with values in there, no graphs. And they actually told me my first visit, they said to me, this readout unit doesn't work. Okay. And I thought, and for the dam owner to buy a new one is a huge capital expense. So I actually went and looked, and I just plotted the pressures, and you could see there's like two sets of pressures, and that's why they said, and they even had the issue of the dates and things like that. If one actually goes and actually check out the typical readings, I actually saw that the typical readings, there's like two sets of readings, and they saw these sort of jumps and thought there's something wrong in the readout unit. If one actually goes and looks at the typical reading and the setting on the readout unit, then there's frequency. There's normally, with these vibrating wire instruments, there's like 3 settings. It's normally the frequency, the period, the F2 or the digit reading, but they're all related to each other. And when these guys on site did the reading, they never made sure this is not like one of the ones where you actually have a knob. This has just got some a pressure that you unit there, and by mistake they would press the unit button, all right, when they take the reading, and they were actually just taking readings, so it was easy. Just, there's nothing wrong with the readout unit, okay? There's nothing wrong with the readings, you just have to convert it, all right, using sort of the typical relationship, all right? And I'll show you guys the results afterwards. So if you this is maybe more relevant if you use a spreadsheet system, but most probably you guys use a database setup, all right? But it's still important to make sure that you store things like your readings, your calibration information, and the results in separate sort of data sets, if I can put it that way. In a spreadsheet, one will actually use a separate sheet in the bigger spreadsheet for that. The other thing, if you do graphing, okay, and that's my take on it, it really helps if you have a time graph, do they have your primary one yearly and the secondary one monthly? Okay, really important. I'll show you now why it's important to do. So this is just, I'll speed up here. So in a typical spreadsheet, but the same in the database, here's all the sort of the inputs that you can have, who's taking the readings, the readout unit value, and things like that. There's actually the calibration setup with your 0 readings. Okay, it's very important, I believe, to have that separately. I see so many people program it in hard, and then the dam owner can't actually see what was programmed into the system. So you can never check whether they actually have put in the right 0 readings when they do the conversion. There's the readings, all right, and it's something like Excel, but is already got some really nice functionality that you can go and set there, that it actually shows you sort of readings that doesn't fit a certain criteria. Okay, there's the results, all right, and there's typically a graph that I was talking about. So in South Africa, this particular dam is for irrigation use, so they actually use the water. So there you guys can actually see the sort of the water level going up and down as well, but it's an arch dam. So the other, except for the water level, the other main like load on the dam is the seasonal temperature change. And it's very important. Well, I just find it much easier to get a feel what's actually happening if you do have a proper scale that gives you like on an annual basis that you see whether you're in summer or winter. Okay. I'm not going to actually sort of talk too much on this, but Manuel has already talked about using the correct constants and the initial readings, but I just want to talk about this concept of zeroing, and we see that a lot. For instance, if you use vibrating wire piezometers, and especially in concrete dams, people will install the instrument, okay, and then only they won't start the readings. Actually, they will leave it there, and then after a year or two, when the dam is finished, would they actually start taking the reading, even if there's no water in it? But then they will zero that reading. They would not actually use it as the actual reading that they get out of there. So let's just, this is Kaorabasa Dam. It's a big arch dam on the Zambezi in Mozambique, 170 meters high. All right, and they actually on the upstream side, they've got some pore pressure meters that is installed either at the surface or like half a meter, and I think 3 meters away from the water surface. So when I got involved with this dam, these ones previously was the people looking at it said they're not working or it doesn't make sense. All right. So if one actually goes and looks at it, so just of interest, if one just goes back, so you guys will see 1, 2, and 3 is actually the high ones, and 4, 5, and 6 are actually low. So if one actually have a water level there, one would expect the pressures at 4, 5, and 6 to be more than 1, 2, and 3, because there's more water pressure there. So if one actually goes and looks there, so 1, 2, and 3 are the red ones, okay? And 4, 5, and 6 are the green ones. So if one actually goes and look there, then one has red ones here that they just doesn't make sense, which is, yeah, and that's what the guys were looking at, and they saw. Then I actually went and just looked at it. What they did was they started after installation when there was already a water level, and they zeroed the result. Okay, so they did not take into account that the actual reading they had was really a pressure. Okay, so if you go and actually convert this, you guys will see you actually get readings that actually make sense. And this part, just, yes, I do agree, it doesn't make sense, but people actually made assumptions during the conversion and during the verification that actually led to the results not making sense. It's incorrect results. Okay. So just the importance of proper interpretation. I'll quickly sort of just to have a few comments on that. So it's extremely important to have a feel for the behavior of the structure when you look at monitoring information. And a lot of people actually struggle with that. So I've seen it many times, dam owners themselves, and at fairly complex dams, they don't want to involve somebody that really understands the structural behavior. They feel they can do it themselves, and then they actually don't do, no interpretation happens of the monitoring information. It's absolutely essential to actually pay attention to during the visual inspection. So I would never do an evaluation of monitoring results without visiting a site. It is, these things are tied together, and me and Manuel have been saying that. Okay, so then, yeah, and this is another one. It was one of Chris's slides, but it comes basically the same. So a lot of interpretation also involves judgment, engineering judgment. And it depends on experience. I showed yesterday that example, and that was just on inspections where I was a young engineer. I didn't know what to look for. And so I didn't see the things that I was supposed to be seeing because I didn't know what it looked like and what to experience. And it's the same with the interpretation of monitoring results. Is a lot of what my knowledge and knowledge base is what I've seen at other dams. You think, I saw something similar at that dam, so maybe it could be a similar problem. Okay, and that's basically my my take on data acquisition and management. Sorry, I think I've taken up the break, but Manuel, you've been basically 15 minutes over.
Yes, we've I think both of us together, yeah, we've used up the break time.
So
It's
I don't know
absolutely if the presentations are quite interesting.
Yeah, but
would
yes,
you guys prefer to have a break, or can we carry on until lunchtime?
I guess if with your permission, if we can continue the session and take the break directly with the lunch break only.
Okay.
Okay. Yeah. No problem. No problem.
Thank you.
You're very welcome. Okay. So now we go for quality flaws and typical monitoring problems and monitoring data analysis. So statistical models and deterministic models and hybrid models, and also a take on dam monitoring software tools. So I'm going to try and let's see. We have, if I remember right, half an hour. Okay.
Yeah, so it's again one of those things that you can speak 2 days on.
Yes, I'll just go. Yeah, I'll fly over the concepts,
Okay.
and hopefully you'll find it useful. So let me go for the for the screen. I hope that you can see the screen now.
Yes, sir.
Okay. So let's go right into it. So quality flaws, some quick ideas, because we've already put into perspective the whole system. But just to remind our goal. So our goal is really to anticipate any issues, any problems, really to monitor potential failure modes. So just that we talked about potential failure modes quite a lot. So really, that's what we want to closely follow and survey and monitor and anticipate. So this timely intervention is essential, and the dam surveillance system needs to help us in this. And in this case, we need to try and tell apart false alarms from real data. And also yesterday, this came up several times. Of oftentimes we say, no, it's not, the data is wrong, or so there's a lot of confusion on a daily basis on whether the data is right, the readout units, if we can trust the data or not. So this thing about quality flaws is very important. We can have issues and circumstances impacting the quality of our data. Many different types. When we are collecting the data, when we are analyzing the data, we're validating it, even when we're storing the data. So always having the raw data and respecting that database, and then the transformed data alongside, but always being able to go back and resort to the raw data, even if it's paper. So with checklist and the tables, that needs to be stored and be kept in a safe place. And nowadays, digitalize that, scan it if necessary. We can have issues with our resources, with our human resources. So organizational problems. We can have technical problems affecting our dam surveillance system. We can have, of course, lots of issues with automated systems. We really have to watch out for automated systems. And we will stress this several times today. And also with the data associated with the sensors themselves, those zero readings. If we have a recalibration, if we need to change the scale or the range of the sensor because maybe it's no longer useful. This is very typical with rod extensometers, even with pendulums. So you need to keep that for the historical database and use different formula for different time periods when you analyze the historical data. Of course, human mistakes, misreading, typos, and also problems associated with the measurement methods. So some quick examples. Plumb lines and inverted pendulums. Just look at these deposits, this calcite and carbonate deposits in the borehole. So the cable cannot really move around these deposits. If we also take a camera and we put the camera inside the borehole, we can see that the cable may be touching the sides, the walls of the borehole, because the borehole is not vertical along all the length. And so watch out for this. because we may be taking wrong measurements and we may be making wrong analysis because the cable is actually touching the wall of the borehole. Also the tanks, we need to refill the oil in the tank. And if we have an automated system like this one, where we have this gauging bars actually touching the cable, just to measure the movement of the cable in both directions, watch out for this, because this can affect the real movement and free movement of the cable. And this is an example. This is a large concrete dam, Itoith, and we had this direct pendulum with this automated system. And we can see that this automated system was really affecting. It was really affecting the measurements. It was really impeding and not letting the cable to move freely. So the piece of advice that I gave in this case is, okay, remove this automated system. You can see this black. So this is really clapping and preventing this automated system from touching the cable so that we don't have this issue. Okay, borehole and rod extensometers. Just look at this one. There's no way you can carry out manual readings to calibrate the automated system. So it's a rod extensometer automated with LVDT, but you can, and this is the bottom of the gallery, and you can't take manual readings over there. Look at this one, same thing. It's automated LVDT, but there's no way you can take manual readings to calibrate the rod extensometers. And just look, these are temperature, rainfall, and pool levels, and just look at the rod extensometers. So some of them are not moving, others show this trend, and then another one is having these jumps and drops, sudden drops in the signal, and then it's going up again and then dropping. So this data essentially is useless. And this is because they were not taking manual readings. They only had automated readings that were affected by these sudden jumps. Just this has nothing to do with the real behavior of the dam. It was caused by electrical and issues caused by the automated system. Watch out for this. Okay, geodetic monitoring. Just look at this dam and this pillar. It was not on ground, on sound ground. So this pillar was moving itself, and it was given all wrong data. So watch out for this and the leveling milestones, especially in earth depth and especially in homogeneous ones. So I've noticed with zoned embankments is not as bad, but with homogeneous earth dams, many of these geodetic campaigns are not consistent. So really watch out for this and try to have different service and on proper ground. And if necessary, just make a borehole and install a rod that is really anchored on sound ground. Okay, inclinometers. Many issues with inclinometers. Just have a look at this reading, and this looks like, okay, we have a landslide at this depth, but it's actually caused because of the casing. So the pipe, it wasn't a proper one, and we can even have with aluminum ones, they can corrode, and we can have holes in the casing of the inclinometer. And this can give us lots of false reading and data issues. So try to go for ABS plastic materials for the inclinometer casings, and really watch out because in many embankment dams, these magnetic settlement systems give us better results than inclinometers. So keep this in mind, because once the dam is finished, the most accurate information is going to come from geodetic campaigns and also from the leveling for vertical. And so analyze this, because inclinometers are very expensive, and sometimes they're really great for some things, but for others, we have other alternatives. Watch out for the expansion joints. And when we're using this in upstream phased CFRD dams and RCC dams, because the casings need expansion joints. Only a month ago, I was inspecting a dam in Africa, and they didn't have expansion joints. So the inclinometers, 3 key inclinometers for the dam behavior were broken down because there were not expansion joints in the casings. So please keep this in mind. And also the measurement intervals, the readout units. So always remember calibration and recalibration with MEMS. Pore pressure and ground water levels. Watch out for these open stent pipes where we measure the phreatic surface because we can have lots of issues in this, also in these cases. When we use vibrating wire piezometers to measure pore pressures, we can have lots of issues. So stray currents and damage from storm, thunderstorm and lightning. So shielding the cables is very important. And earthen, our electrical systems have to be earthed, and we need to have surge over voltage and surge protections, because this is a huge problem. And the cables oftentimes are sliced. They're not properly armored. Also, if we have a Casa Grande piezometer clogging, and also in vibrating wires, the filter, remember the low air entry and high air entry, corrosion of the wire and the welding, the temperature compensation, and the barometric compensation. That was in that previous presentation on sensors. The barometric correction is incredibly important, especially if you have the fully grouted method. You really need to carry out the barometric correction. So just look at this piezometer. This is the reservoir level, the blue line. And this is the piezometer, which, yeah, it makes sense. It's going along with the reservoir level. And suddenly, at this point, the piezometer goes crazy and starts with this trend, increasing trend. Of course, it goes beyond the crest level. I mean, the pool level, the reservoir level, but even the crest level. So this drift in the signal, this is very typical, and it's caused by a poor quality piezometer, where the wire, the diaphragm and the wire is not properly welded, and the material and the alley of that metal is not a proper one. So watch out, because there are many different types of piezometers, and the price range is huge, and this is an issue. Watch out for this. This is the reservoir level, this blue line. And watch this piezometer. The piezometer is going up and down, crazy. So the thermistor, and it was not being properly used to correct and compensate for temperature measure, and also the barometric pressures. So look, you can see this is 2010 and this is 2018. So throughout the years, this piezometer has given us data that is useless. And just watch this, 2018. So a creature the engineer creature goes there in 2018 and analyzes and finds out that for almost 10 years, because this goes back in time, the data is useless. And nobody noticed this. So watch out for this. Okay, total pressure cells. That can be very useful and very important to have the total stress and that way finding the effective stresses. But they need to be properly installed and many conditions need to be met. So the compaction operations around the cells, how you install physically the total cells. So this is a good example. This is an example of pressure cells given at great readings. So this is the temperature, this is the pool level, rainfall up here, and these are the pressure cells, and they're given excellent results. So this is an example of a success story, but I have to tell you that 90% or 95% of the times when I look at total pressure cells, the data is useless because of poor installation procedures. And so this is not usually the case because many things need to be looked for when we are installing total pressure cells. And maintenance. So with quality flaws also, it's very important to have within our operation and maintenance program a surveillance system maintenance program. Because our surveillance systems, they also need to be maintained if we want to have data quality. Sensors and readout units, they need periodic calibrations. We need to watch out for water, dirt, lack of proper lighting. We've mentioned this already. And really surveillance must be part of the O&M programs. Okay, so let's move on to the monitoring data analysis. So what we do to just analyze the data. So this is another chart, another flow diagram, very similar to one of the flow diagrams that Louis showed you in the previous session. This is another perspective. So this is from the O&M and quality data perspective, but focusing on on-site, hands-on ground issues. We're going to collect our data, and we're going to consolidate the data. So reduct. The data reduction is turning the raw data into physical measurement. So taking the hertz, the frequency, and turning that into pressure. So kilonewtons divided by square meters, for example. So that's data reduction, filtering, and analysis. We're going to go for the safety reports. We're going to come up, once we have the safety reports and we've done all this homework, we're going to recommend things in our dam safety reports. And there's going to be recommendations for O&M because the surveillance system is part of the operation and maintenance program of the dam. And in these dam safety reports, we have to come up with recommendations on what to do when a sensor seems to be giving us faulty data, and also the automated system. And we need to be able to give specific recommendations for sensors and maintenance tasks. And that's going to inform our field work. So our field work planning is going to be informed by all this along the way. So the key elements for a proper operation and maintenance. We need to identify the tools that we need to check and do the maintenance of our sensors. So maybe we're going to need a laptop. Maybe we're going to need the manual reading measuring device to calibrate, and we're going to need patterns. We're going to need checklists, very important, and always tell apart manual and automated readings. Go for the calibration and have this in a plan. Okay, we need to calibrate the automated system at this date. We need to measure the pattern before we do the inclinometers and the joint meters. Before every measuring campaign, measure the pattern. And always, again, we've mentioned this, the main issues: water, moisture, humidity, proper lighting. This is going to affect the quality of our data. So when we go for the data analysis, very quickly, basic questions. Why do we want to have the dam surveillance system? What do we want to inspect, implement, and measure? What do we have to monitor and survey and inspect visually? And how to do it? We need to have procedures, checklists, databases. So this has to be planned and designed properly. We need to think of this. Watch out for automated systems. They can never, ever replace visual inspections and manual data collections. And certain things need to be accomplished when we implement an automated monitoring system. They can be very powerful and very useful in dams in remote areas, dams with critical safety issues where we need real-time data. So they can be very powerful, but they can never replace calibration, visual inspections, and manual. And certain things need to be accomplished. Some additional key questions by the dam system. Is the dam behaving as we expected? Is the dam behaving as it did in the past? Is there any trend in their behavior? Is there any flaw or any anomaly that we are detecting in our data? And finally, and in our safety reports, is the dam safe right now, as of today? And how safe will the dam be in the future, in the short term and in the long term? We need to answer these questions with our dam surveillance system. So how do we analyze the data? Well, we can use deterministic models developed beforehand with a physical basis. We can use statistical models and machine learning with neural networks and boosted regression methods and forest and fuzzy logic and all these things. We're addressing this in a bulletin in our committee. The important thing, this is developed in hindsight. Once you have at least 5 years of robust and reliable data. So you do this afterwards, you do this beforehand, but you can calibrate and use both worlds, take the best of both worlds and combine a deterministic with a statistical model and come up with a hybrid model that can be updated. So the monitoring data analysis, so good old graphs and plots. So we can have lines with the same temperature in our dam, and we can use these drawings to help and do the analysis of how the dam is behaving. We can have this time series where we have pool levels, reservoir levels, the temperature, the rainfall. So these are years. So this you can see this is years, different years along the way, and then we can have here the time series. We can use different types of drawings. Okay, this is where of course this is a deformed scale, but where the pendulum cable, the location in different years and times of the year, we can use these profiles to see where the cable was located in both directions in different sessions, seasons, and moments of throughout the year, and also in the history of the dam. You can see the pool levels. Here are different colors, and these colors are these lines, and you can see where the dam was positioned. For piezometers, we can have these profiles with the uplift pressure law in the foundation, and then we can have this front view with the actual absolute piezometric level for these piezometers, and each block we can see how the block is doing, and then the reservoir, the pool level at a certain moment, and then each piezometer, the total absolute piezometric head. We can have for joints, so joint openings, we can have the strain gauges in the concrete and come up with the principal stresses diagrams like this one to see how our arch dam is behaving. We can have correlations between seepage and pool levels, and we can see if we have any trend that it's not linear or that skyrockets. So seepage that skyrockets when we reach a certain pool level. And we can have these diagrams for total cells and to see the pressure and come up with the also the effective stresses. We can have these lines with the same pore pressure in the core and the foundation to analyze piezometers in an embankment dam. We can have campaigns where we have, this is the crest. This is different milestones along the crest, and every line is a date with a topographical leveling campaign. And we can have drawings where we place our visual inspections because we want to track down and report our visual inspections. So many different ways of portraying and treating the data. Then a quick reminder. So the deterministic models are this, like a FLAC, ANSYS, SAP 2000 deterministic model, or we can have also geoslope type models. So these are deterministic models, and then we have the statistical models, where we have a mathematical formula. We analyze data in the past. We come up with a multiple regression that accounts for pool levels, temperature, gradients, changes, and we can come up with even the residual values. So we subtract the real values with our model, and we can analyze this way trends. And combining statistical models and deterministic models, we come up with hybrid models. And finally, just a quick comment on dam monitoring software tools. Because these are very powerful tools that we have at hand, but certain things need to be accomplished, and we need to keep in mind these questions that I just showed. Our goal is to know if the dam is safe enough today, and it's in the short term and in the long term. And we have to do some homework if we want to use a software tool. We need to make an inventory of all our sensors, the naming of our sensors. We need to do a lot of field work. We need to relate this with a monitoring plan. We need to upgrade many things in our system. If we implement an automated system and software tool, we got to keep in mind that it needs to be maintained. So upkeeping this is an investment. So we need to have money every year to make sure that this is going to be properly maintained. We need to upgrade the system from time to time. We're going to have several functions, and to implement the software tools, we need to software, hardware, communications. We need to set it up and commission it, and we need training. So all of these things need to be accounted for. And just keep in mind, until we get to the software tool, we can see on our screen or on our mobile phones, there's a lot behind that. We have the sensor, we have the multiplexers, we have the signal converter from analog to digital. We have the data logger. We have the telemetry. So we're going to use some communication systems to convey and transfer this data that's been converted from analog to digital to our CPU, to the central processing unit. And eventually we're going to have these software tools that help us to do the data management and to visualize the data. So these software tools, we have many different components and elements: dashboard, real-time display, trend lines, alarms for thresholds. We're going to have all the naming, and for instance, a piezometer, it's going to have different variables. The piezometer is going to have the frequency, it's going to have the inverse of the time. We're going to have the pressure, we're going to have the total absolute piezometric level. So one piezometer is going to give us at least 4 variables in our software tool. We're going to have a lot of things to store the data, FTP transmissions. Then we're going to have all these tools to analyze the data. So all these data analysis options that I've shown you. So correlation, intensity plots, histograms, different types of plots are going to be at hand. Relative plots, overlay graphs, burst data, profile views, just like what I showed you. And then we're going to need to implement in these software tools elements to validate our data, to include nodes. We can even relate this software tool with webcams and security. We can be able to download and create files and send files and share data. And we're going to have to be able to change data, so import and input data. We're going to need an interface and user profiles. Maybe somebody is going to be able to read something and access parts of the software tool, and other people only to see the data and not make changes. And nowadays we have lots of different options and tools in the market at hand. And that's it. So this is again another long presentation where we could spend the whole day on this, but at least you have an idea of these quality issues, data analysis, and these software tools. And if I remember right, we've gone a little bit into the lunch break, but yeah, we've covered. So these first sessions, these 3 sessions have been very intense. A lot of information thrown at you. But I think after the lunch break, yeah, we'll show you some real examples of data, and we'll have some time for discussion so that you can hopefully, take part, and don't be afraid to make comments, ask any questions, whatever. And so after the lunch, I think we'll have some room for, after these 3 sessions, they've been a little bit exhausting. But yeah, we'll have some time for discussion after the break.
Thank you.
And
Yeah,
I think we have an hour and a half. Well, an hour and 20 minutes or so.
Yes, we do have. And thank you, Dr. Manuel and Mr. Luis, for making a detailed and excellent presentation for the first half. Now we'll take a break, lunch break, and reassemble at 14:30 hours IST, around 1 hour and 25 minutes approx.
In 25.
Yes. See you after the break.
Good.
Okay. Thank you very much. And then see you after the break.
Yes, see you.
See you.